Welcome back. Alright, what I've done here is I have summarized what we have seen so far of the natural carbon cycle, where I have drawn 4 reservoirs of carbon dioxide, the land biosphere, the atmosphere, the mixed layer, and the deep ocean. And I have given the size of their inventory, or their reservoir of carbon dioxide, of carbon, in each of those little hexagons there. And then I've drawn arrows showing the transfers of carbon between those different reservoirs. And we can see that there are transfers in each direction, and it works out that they're all right around 100 gigatons per year. Alright, so you have a very similar diagram to this in your textbook. Now, if you have molecules of carbon, with organic molecules, carbon dioxide and so on in the atmosphere or the land biosphere or whatever, there is a turnover time. How long an average molecule or an average atom of carbon will be in the atmosphere before it moves either into the mixed layer or into the land biosphere. How long an average atom of carbon dioxide will be in the deep ocean before it is transferred back up into the mixed layer, etc. Your textbook prefers the term turnover time for that. If you stick around for ATS 113 in next semester or whatever, that textbook prefers the term residence time. I think your textbook once or twice slips up and says residence time or even lifetime. These are all ideas, though, of like how fast does carbon go in and out of these different parts of the system. And it's related to both the size of the reservoir in terms of how much carbon it's storing and the rate at which carbon is going in and coming out of each of these reservoirs. And what I did here is I actually put the residence times as provided by your textbook onto each of these 4 reservoirs. And you can see that the average residence time, for example, in the atmosphere is 3.7 years. I'll tell you something that's coming up if you stick around for ATS 113. In ATS 113, there's actually a problem where you compute the residence time for carbon dioxide. And in that problem, the problem is very clear that says the math of actually computing this, we faked the number so that it comes out to a nice round number. And I think it comes out to 100 years. Okay, you can see it's not actually terribly realistic. It's more the process of computing the residence time that matters in that problem. The right answer is about 3.7 years. Any given carbon molecule that's up there in the atmosphere, on average, will be in the atmosphere for about 3.7 years. And that's in contrast to, say, the land biosphere, where the average carbon molecule will be, a carbon atom will be part of the land biosphere for about 20 years before it is returned to the atmosphere by respiration. There's other processes that can return it to the atmosphere, like burning a forest, for example, would convert the carbon that's in the form of wood and things like that back into carbon dioxide that goes in the atmosphere. Same with like the deep ocean, it's about 380 years. That's about how long those materials, after sedimenting down from the mixed layer down into the deep ocean, take before they are recycled back up by currents and upwelling and so on back up into the mixed layer. And you can see all these numbers here. Memorizing the numbers in and of themselves is not so important, so much to understand that there's a very big difference in the rate at which carbon is exchanged and how long the turnover time is for carbon in each of these reservoirs. The atmosphere exchanges carbon relatively rapidly with the land biosphere and the mixed layer, and it's about 100 times more slowly than, say, the deep ocean does. This is going to have implications for how we're going to be able to address climate change and so on that we'll see later in the course. Now, there's one other giant reservoir, though, for carbon in the Earth atmosphere climate system, and that is the rock, the lithosphere, to use the right word, the big ball of dead rock. Rock contains a lot of carbon. Carbon is stored in the minerals that makes up different kinds of rock, or different kinds of fossil fuels, and all kinds of things that are in the big dead ball of rock. The book uses the classic example of limestone. Limestone is CaCO3, it's got carbon in it, and like you can see, there's carbon, there's limestone there on those cliffs that the guy is kayaking by. That's a picture of the Indiana State House. I just thought there's a nice picture of a limestone building. I think St. John's Church on Creighton's campus is a limestone building, if I'm not mistaken. Limestone is dead rock, and it's made of a mineral that contains carbon. So if we have another reservoir here, it would make some measure of sense if we could say, oh yes, and we have this many gigatons of it. It's millions and millions and millions. We don't know how many gigatons of carbon there are in the lithosphere, the big ball of dead rock. I mean, there's coal and limestone and natural gas and oil and zillions of other minerals that contain carbon. So it's big, okay? The total amount of carbon that's in the ground is big. Thousands and thousands of times more than there is in the atmosphere or in the biosphere or whatever. So where are we going to put that on this diagram here? If we have our little diagram here that's been summarizing the natural carbon cycle, where do we put this? Well, the way the book did it is actually pretty slick. They just sort of grouped all the things we've seen before, where the carbon is either in the form of something alive, like the land biosphere, or it's very quickly exchanging with things that are alive. I mean, the carbon that's in the atmosphere isn't alive, it's in the form of carbon dioxide, but within 3 years or so, it's going to be picked up by plants and used in photosynthesis, or it's going to be dissolved in the ocean and be used by critters there as part of their, their food cycle and so on. So if we just sort of put that dotted line around everything we've seen before and said, that's one part of the carbon cycle, then we have rocks over there. And rocks over there on the right are just millions and millions of gigatons. We don't know how much there is. And it's dead, and it's just sitting there under the ground. And there are exchanges between the lithosphere and the big dead ball of rock and the rest of the carbon cycle, but they're relatively small in the natural world, only about 1/10 of 1 gigaton per year, as you can see on this little diagram here. There are ways in which carbon is getting from the biosphere, atmosphere, ocean system into the rocks, and there are ways in which carbon is getting out of the rocks and back into the life cycle on the surface of the Earth, but the rate is really quite slow. How it actually happens is kind of a set of interesting processes. How you get carbon in the natural world from rock forms into the atmosphere is principally through the formation of volcanic eruptions. I know when you picture a volcanic eruption, you're mostly thinking about lava and things like that, but actually a huge amount of the total material that comes spewing out of a volcano is carbon dioxide. I don't want you to get the idea like the inside of the Earth is hollow and there's like big bubbles of carbon dioxide down there. It's dissolved into the magma, and when the magma comes near the surface of the Earth, it starts bubbling out in much the same way, the carbon dioxide bubbles out of a bottle of Pepsi or something like that, okay? But yes, the primary way in which we get, in the natural world, we get carbon from the rocks back into the atmosphere is through volcanic eruptions. Getting carbon back from the atmosphere into the lithosphere, into rock, is a little bit more complicated. It is largely predicated on the idea that we're going to be forming acid rain. Carbon dioxide in the Earth's atmosphere dissolves into raindrops, making a weak carbonic acid solution, very much like what we did in the ocean with ocean acidification. This carbonic acid falls onto the materials at the surface of the Earth, like rocks and plants and so on, partially breaking them down and forming organic materials like calcium carbonate and so on, that then can flow down rivers into the oceans and so on, and eventually get deposited on the floor of the ocean. Now, once those materials are on the floor of the ocean, I mean, if they're easily dissolved in water and so on, they might come back up in the form of upwelling and so on, but some of it's going to stay down there on the bottom of the ocean in the form of these organic materials, carbon-containing materials, that don't dissolve all that well into water. And the spreading of the seafloor on geologic timescales, we're talking like continental drift and so on, will push those materials, like I showed in that diagram there that came from a, junior high level textbook of geology. As the ocean crust is pushed by plate tectonics and then subducts down under the continents, you can see how it carries those materials down deep into the core of the Earth. That is an important way in which we can take carbon out of the atmosphere, put it into raindrops, carry it out to the ocean, deposit the carbon at the bottom of the floor and things that don't really dissolve all that well, and then carry it, let it ride the ocean floor down as it subducts under continents. And that carbon is just gone, okay? It's down deep into the Earth. Yes, it might come back up in the form of volcanic eruptions and so on, but that carbon is, for a long time, just out there into the big dead ball of rock. Another way that we could do this is by the formation of fossil fuels. What I have here is a picture of a guy, I don't know if you've ever seen how coal is mined, but it forms in these layers called seams. That's a coal seam right there, that big black thing that's maybe 3 times as tall as the man. And they are going to be extracting that coal using bulldozers and backhoes and things like that from that layer. Coal seams form when plant material gets buried by other sediments before it gets a chance to completely decay. And then under extreme heat and extreme pressure, under the weight of all the rocks that form on top of them, the plant materials over the course of millions of years convert into fossil fuels like coal. That is a huge coal seam, what you see right there. That's much taller than that guy. I wanted to take the class on kind of a digital field trip to a coal mine that's fairly near where I live in Indiana, but it is actually in the process of closing, and they're a little bit leery of anybody coming with a video camera right now. But the coal seam, I actually know a guy who's a miner at that coal mine, and the coal mines in Indiana, the seams typically are about 6 inches to a foot thick. Okay, so whereas this is, a 20-foot probably thick coal seam right here, that's in fact kind of an unusual thing. I mean, coal seams tend to be kind of a narrow layer like that they just extract the layer from. And petroleum and natural gas, they form in similar sort of situations where plant material is buried before it gets a chance to completely decay. This total land, surface, ocean process has a total turnover time of about 400,000 years. A given carbon atom that's currently part of your body, part of a rainforest, part of the carbon dioxide in the Earth's atmosphere, the average carbon atom will end up in the cold, dead ball of rock that is the Earth's lithosphere on average about 400,000 years from now. Okay? Though the turnover time is pretty long. Okay, we pretty much know how much carbon we're dealing with in the natural land biosphere, atmosphere, etc. Because, I mean, it's on the scale of hundreds of thousands of years that those atoms stay in that part of the Earth system. In contrast, the turnover time for the lithosphere, the rocks, is on the order of billions of years. If some limestone that contains carbon in the form of CaCO3 gets into the ocean and gets carried by plate tectonics by the floor of the ocean, and it gets subducted under a continent, the Earth isn't old enough for most of that carbon to ever come back. Okay? Most of that carbon is just down deep in the magma of the Earth, and we will not see it in the lifetime of the solar system. Okay? This is actually really interesting and important because, I mean, again, when we talk about climate change and stuff like that, now we have a very different set of timescales. It's hard to think of 400,000 years as fast, but in fact, the surface of the Earth's exchanges of carbon are much faster than what's going on in the ball of rock. Now, I'm drawing it, and I circled it in yellow there, like there's a perfect balance here. Like the cold, dead ball of rock that is the Earth absorbs about 1/10 of a gigaton per year of carbon and emits about 1/10 of a gigaton of carbon per year back in the form of volcanic eruptions and so on. In practice, there's actually a small imbalance there that's hard to measure on human timescales. But over the course of billions of years, it's actually essential to life on Earth. Over very, very long periods of time, the small imbalance between the amount of carbon going into and out of the rock makes a huge difference, because we are slowly transporting carbon out of the atmosphere, biosphere, ocean system, and into the rocks. Slightly more carbon goes into the rocks than comes out of the rocks each year. If you can go back into the paleoclimate record, what you find out is, if you go back not like to the last ice age, which is merely 100,000 years ago, but if you go back like tens of millions, hundreds of millions, billions of years ago, what you find out is the earlier atmosphere, farther back you go, the more and more carbon dioxide the Earth's atmosphere had. Which actually turns out to be necessary for life on Earth, because over the age of the solar system, the sun is putting out more and more energy. If you go back, a billion years ago, the sun was putting out about 25 to 30% less energy than it does right now. Just part of the natural life cycle of a main sequence star like the sun. Well, if the sun was putting out like 25% less energy, how come the Earth wasn't just a frozen dead ball? Well, it wasn't, because of all the carbon dioxide that was in the Earth's atmosphere at that time. Now, over the period of billions of years, as the sun has gotten brighter and hotter, in order to keep the temperature of the planet in a range that's useful for life, slowly life has moved carbon out of the Earth's atmosphere and into the into long-term storage in the form of like rock getting subducted under continental plates. I don't want you to get the idea that like this is happening like somehow other life knows to do this. It's more a matter of we wouldn't be here if life weren't doing these things, okay? Life as we know it wouldn't be possible if the Earth's atmosphere still contained the kinds of carbon dioxide concentrations it had earlier in Earth's history, just that it needed to have in order to keep the planet in an appropriate temperature range for life to exist. Cool! Alright, the natural carbon cycle is not terribly complicated. It's going to be the mess of the ways in which humans mess with this carbon cycle that we're going to worry about. Before we get to that though, let's actually talk about a couple more questions here. Which of these reservoirs of carbon had the shortest turnover time? The atmosphere, the mixed layer, the deep ocean, or the land biosphere? Alright, think about that. Maybe look back through your notes. Choose one of your 4 options below, and we'll get some feedback before we move on to question 5.